So next, we're going to take a look at example number 31 or EX31 from my Java 8 folder in the live lessons GitHub repository. So here we are in the EX31 project in the EX31 file. And we'll see that this particular example shows how Java's volatile type qualifier can be used to enable two thread objects to coordinate their activities. In particular, these two thread objects are going to alternate printing ping and pong. And you can find more information about this particular technique at this link on the dzone.com website. So this is a really fun example. It's really interesting to see how volatile works. And I think this particular code snippet, this particular piece of code we're going to look at will demonstrate these features very nicely. So here is a volatile variable called mval that we're going to share between these two thread objects. And you can see it starts out with a value of 0. So it's a static volatile long. And then we're also going to have the number of iterations we want this thing to run. And it's going to run 5 times, printing ping 1, pong 1, ping 2, pong 2, ping 3, pong 3, and so on up to ping and pong 5. So here's the main entry point. To run the app, we play ping pong. Here's the play ping pong method. And we're going to define two threads. The first thread is going to be the pong thread. And this thread is going to have a runnable lambda, which we're going to look at, that reacts to changes to the mval volatile field. That's what it's waiting. It's basically kind of listening, using that word loosely, for that field to change. Actually, it's spinning, waiting for it to change. We'll look at this in more detail in a second. Then we also have another thread we create called the ping thread. And by the way, you can see I've named these threads. Here's the ping thread, here's the pong thread. So when we print the values out later, you can see which thread is doing which thing. This has a runnable lambda that changes the value of the mval volatile field on each loop iteration. So let's start with this one first, and then we'll come back and take a look at how the pong thread is behaving. So keep in mind, when we create and start these threads, they're both going to start running at the same time. So what this thread does is it has a for loop that keeps looping until LV, which just stands for loop variable, is equal to S max iterations, which is 5 in this case. We start by atomically reading the value of LV, which is the loop variable, loop counter, from mval, which is the volatile variable. Because it's volatile, we can read it atomically. And we're going to keep going while we haven't reached the number of iterations. What we're going to do is we're going to increment LV by 1, so we can say ping 1 and so on, not ping 0. And then we print that to the output. And then what we're going to do is we're going to set the value of mval, that volatile field, to the loop variable's value. So it started out at 0. Now it's going to be to 1. And now we're going to set this to 1. And that's going to trigger the pong thread to do something. We'll take a look at what it does in a second. Then the ping thread is going to pause for 1 second to give the pong thread a chance to run. If we didn't pause here, if we just let ping iterate through 0 to 5 or 0 up till 5, we would be done very quickly. There would be no ping pong. It would just be essentially ping, 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 and we'd be done. And that thread would die. So we don't want that. So we give a little chance for the pong thread to do its thing. Here's what the pong thread does. Now the pong thread it's a spinning Jenny. It's going to spin like mad. And so what it's going to do is it's going to keep spinning until LV equals S max iterations. But it's only going to increment LV every time mval changes. So here's what we do. We start at LV at 0, just like we did down here. So this starts at 0. And we're going to also keep track of a spin counter. And we're going to keep spinning till we're equal to S max iterations, just like we did below down here. The difference being that the spins are going to continue. And you'll see they're going to be hundreds of millions, if not billions of spins between these calls, because we're sleeping for about half a second. That shows you how fast these computers are. So what's going to happen here is we're only going to run the body of this if statement, which is going to update the values if the value of LV doesn't equal the value of mval. And at first they'll be the same value. They'll be 0. So it's not until the ping thread increments this by 1 and sets to mval atomically that the if statement will be true. So whenever the values aren't equal, we then print out the pong. So now we can print the value of this thing as ponging. And we also print out the number of spins that this loop went through until it saw that change in the value of mval. We then go ahead and atomically read LV from mval, which will increment it by 1, and we reset the spin count. So that's the way this is going to work. You will notice that there are no locking operations here in the sense of there's no semaphores, there's no reentrant locks, there's no condition variables. There's just a volatile field that's being shared between these two threads. So let's go ahead and run this program and you'll see what it does. And you can see it's printing ping 1, pong 1, ping 2, pong 2, and so on. And in addition to pinging and ponging in an alternate way, which is what we want, you can see it also tells you how many times the pong thread spun before it got a chance to see that the volatile variable or volatile field mval had been updated. So I think I mentioned billions of spins are taking place in that half second. So this is kind of interesting because it demonstrates how you can use atomics as a form of lock-free synchronization. And it also shows you the importance of volatile. For example, if we come up here and we comment out volatile, so this is no longer a volatile field, that means that when we set or get this value mval, then it's going to not have been propagated. So as you can see here, it's actually warning us. It's saying, hey, this thing's always false because the value of mval, when it's not made volatile, will not have to be moved out of the cache that it's running with the core. So to demonstrate that, let's run the program, and you'll see it'll probably just print a bunch of stuff. You can see it prints mostly pings. And then pong ran 1 time, and that was it. And now the program is hanging because it wasn't actually alternating, and the values that were being updated, any changes to the mval field is not being propagated between threads because it's not defined as volatile. So the key thing about volatile, remember, is that volatile ensures atomic reads and writes, and it also ensures that the memory is made consistent. So that's the really key point there, that when you do these atomic reads and writes, as a side effect, it makes the values visible to other threads. Essentially, it flushes the cache. That's the way to think about what's happening under the hood. And this is all taking place, of course, at the level below the Java virtual machine, but the Java virtual machine is aware of how these things are actually working under the hood. So really fun example that demonstrates how you can use volatile in order to be able to coordinate the activities between threads. Now, having said that, is this a good way to do things? The answer is typically no. There's usually better synchronization and, more importantly, better coordination mechanisms, especially things like condition variables that would work well for this type of task. However, one of the virtues of this approach is there's no locking going on. And so for certain applications where you really need to get very, very fast notification and you're willing to expend a few extra cores to spin a lot, this could be something that you might want to consider. In fact, there's a whole branch of synchronization theory and practice dealing with lock-free synchronizers that use this kind of an approach. And likewise, if you take a closer look at the Java concurrency libraries, you'll see that they use an approach not unlike this, oftentimes to very quickly check to see if they can get access to some shared resource without blocking or going to sleep. And if they're only blocking or going to sleep if they can't get access to it. So this kind of an approach is a very common approach. And you'll see if you look at the source code for the Java class library with concurrency in particular, see a lot of use of this type of idiom.